Hello everyone, and welcome to today's Chem lesson. Today, we're going to talk a little bit about collision theory, which is the running theory for how reactions occur. Right, we've talked a lot about the reactants and the products, right, what it takes to go on the left side, what you need to go to the right side, but what we've never talked about, what we've never spent time looking at, is the middle, right? What does the arrow represent? Right, when we're talking about a reaction, we know that, X and Y come together to form a new product, XY. But how? Collision theory is the theory that talks about how we go from reactants to products. Collision theory states that in order for a reaction to happen, the reactants, the particles involved, need to collide with the right amount of energy at the best angle. Right? They need the right amount of energy and the correct angle in order for that reaction to happen. When we think about that in terms of chemicals, it's a little bit complicated, a little bit tough to picture, but how about instead you think about a high five? In order for a high five to happen, the two hands, the two involved people, need to hit at the right angle with the right amount of energy. What if one of those things is wrong? Think about it. What if you have the right angle, but not enough energy? Right? You gently lay your hand on top of your friend's hand. Not a high five, right? Definitely not a high five. What if you have the wrong angle? Right? You go in for your high five and you just miss. Right? Your angle wasn't correct. Right? That's also not a high five. You need the right angle, you need the right amount of energy, otherwise you do not get the result, you do not get the product that you were hoping for. The same thing applies to our chemicals. In order for X and Y to become XY, they need to hit each other, they need to collide so that they can form that bond, and they need to have enough energy when they collide for the bond to form. Right? They need to break apart any existing bonds and create new bonds. We can speed this up, we can slow this down, and what we do when we are speeding up or slowing down a reaction is we are influencing those two categories. We are making those two particles collide with more energy, or we are influencing the angle. And now we can't really influence the angle because molecules, atoms are too small for us to, take and align them, right? They're not Legos where we can take them and make sure that they line up in the right way. But what we can do, right, we can't influence the angles. What we can do is influence how many collisions there are. The more collisions there are, right, if you try 20 high fives, if you try 30 high fives, 40 high fives, 50 high fives, 60 high fives, right, the more you try, the better the odds are that you get a successful high five. Right, so we can't influence angles, but we can influence number of collisions. We can influence energy because energy is just temperature, right? We can increase the temperature and we can increase the number of collisions. Or, alternatively, we want to slow down a reaction, we can decrease the temperature and decrease the number of collisions. And there are a couple of different ways that we can do that. Specifically, a number of different ways that we can influence the number of collisions. Let's look at those. There are 5 different factors that we can use to influence the rate of a reaction, to increase the amount of successful collisions. The first is changing the concentration. If you increase the concentration, you increase the amount of collisions that happen. And like I just said, the more collisions that happen, the better the odds are of those substances colliding at the right angle. On the other hand, if you decrease the concentration, you decrease the number of collisions. Right? These particles need to hit each other, and if there's a lot of them in a small area, the odds of them hitting each other are a lot higher. But if there's only a small handful of them, right, if I erase most of these, if I just put 5 particles here, the odds of these things hitting each other are much lower. The more particles present, the more collisions will happen, the better the odds of a successful collision happening. The second thing we can do to influence this is by increasing or decreasing the temperature. Temperature does 2 things. One, it gives the particles more energy, like we said on the previous slide, right? That's one of the factors you need. You need the right amount of energy. The second thing it does, increasing the temperature, changing the temperature, is influence the number of collisions. Because again, think back to what temperature means. Temperature is a measure of how quickly the particles are moving, right? Temperature is a measure of average kinetic energy. The faster the particles are moving, the more likely they are to collide with each other, right? Even if there's only a few of them, right? Let's go back. Let's erase some of these, right? Now we've got only a couple of particles. If it's moving nice and slow, the odds of it hitting something, they're pretty low. But the faster I make this particle move, the more opportunities it has to hit other things. Right, so temperature does both. Temperature increases the amount of collisions, right? Everything is moving faster. They're moving more, they're going to hit each other more. And it increases the energy that they collide with, right? Because temperature is energy. The third one is our surface area. Increasing the surface area increases the amount of collisions. And this now connects back to when we were talking about dissolving stuff. Right? When you want something to dissolve, you want it to have the most surface area. You want the most interaction between the thing you're dissolving and the water. Right? That was a sneak peek of this. Right? This is where that comes into play. This is the reason that comes into play. If you increase the surface area, right? Let's use dissolving as an example. If I have a sugar cube and I put it into a cup of water, the water can only interact with the outer layer here, right? The surface area of that substance. But if I crush that thing up and I make a powder of it, there is a lot more area for the water to collide with, right? Think about a water molecule moving this way, right? Versus water molecules moving. They have to hit this as they move, right? The greater the surface area, the greater the number of collisions. The greater the odds that one of those collisions is a successful collision. Now the fourth one is a new concept, right? The idea of the nature of the reactant. All right, let's talk about that a little. Let's look at this reaction. Right, if I'm looking at this reaction and I want this substance to react with bromine, and I want it to become bromated, and I want to break that double bond and replace the double bond with the 2 bromines. If I want this to happen, The bromine needs to collide with a very specific part of this molecule, right? This is the good set of angles. Anything approaching this way is good. That will happen. But what about this angle? This is a bad angle. This is a bad angle. This is a bad angle because it does not interact with the double bond. Right? All of these bad angles are there because this is a big complex molecule. Right? I do not have a perfect 360 of good angles. I have roughly a quarter, right? Roughly 25% of these angles are good angles. Now compare that to something like two ions interacting, right? An Ag and a Cl minus becoming AgCl, right? Forming that insoluble substance. There is no bad angle on a sphere, right? These are both spheres. It doesn't matter where they collide with each other. If they do head on, if one comes at it this way or this way or this way or this way, right? No angle is a bad angle, right? This has full coverage of good angles. You're not worried about the appropriate angle for an interaction like this. All you care about is, does it have the right amount of energy? And this is why when we do chem in the lab, we don't often do big organic reactions. A lot of the time we focus on solution chemistry, because solution chemistry involves these ions, where there is no bad angle, so that happens much quicker. Right? An organic reaction can sometimes take hours to happen. If you go to a research lab in college, you set up your reaction, you let it run for 30 minutes, 40 minutes, and you check on it. Or for some of the more intense ones, you set it up, you leave, you go to the dining hall, you get dinner, and then you come back and you check on your reaction an hour and a half later to hope that it's done. Right? The more complicated your reactants are, the longer your reaction takes, because you are hoping for the good angle. And if you don't get the good angle, you gotta wait until these things collide with enough energy at the right angle to form your product. Last but not least are our catalysts. Catalysts lower activation energy. And activation energy is the energy required to start your reaction. And by lowering activation energy, they lower the amount of energy that is needed to start that reaction. And they make it easier for that reaction to start. Right? Catalysts have no real impact on angles, right? We're not really talking about angles when we talk about catalysts. Right? When we talk about catalysts, we're talking about activation energy. We're talking about what is the minimum amount of energy required to start this reaction, and how can I make that even lower? Right? Instead of costing 15 kilojoules worth of energy, now it costs 10 kilojoules worth of energy. Right? An easier target to hit, an easier threshold to meet. Therefore, an easier reaction to start. What about a practice problem? How about that? What if we looked at a question like this one? As the number of effective collisions between reactants in a chemical reaction decreases, the rate of the reaction does what? Decrease, increase, or remain the same? If we're looking at collisions and we're saying that there are fewer collisions, that means that the rate of this reaction will decrease. Fewer collisions means fewer successful changes from reactants to products. The rate of that reaction slows down. You have to wait longer before you are finished with it. And as we continue through this unit, as we talk more about kinetics and equilibrium, we are going to focus on this idea that effective collisions with enough energy at the right angle make a reaction happen. But, as for collision theory, that's really the gist of it. So we're going to stop there for today. I'm going to tell you all, or ask you all, to have a fantastic day.